Good morning, students. Welcome to the class on advanced organic reagents. We will discuss Corey-Fuchs reaction in this class. What is Corey-Fuchs reaction? Conversion of aldehydes into 1,1 dibromoalkene, which will be further converted into alkyne. It is called Corey-Fuchs reaction. So overall conversion of an aldehyde into alkyne triple bond is called as Corey-Fuchs reaction. We will use 4 equivalents of triphenyl phosphine, and 2 equivalents of tetrabromomethane. So this reagent will convert aldehyde into 1,1-dibromoalkene. Then we will use N-butyl lithium, a strong base, 2 equivalents, followed by we will add an electrophile, either H plus or any other electrophile. So a carbonyl aldehyde will be converted to 1,1-dibromoalkene by treating it with triphenyl phosphine and tetrabromocarbon. Then when we treat it with a strong base, this will be converted to an alkyne. Now we will look at the mechanism how this transformation will occur. We know the Abujov reaction, right? Formation of carbon phosphorus bond. But here the same formation of carbon phosphorus bond will occur in a different fashion. Phosphorus will attack on bromine. Carbon generates a negative charge. Then we have triphenyl phosphine bromide. Now this negative charge will attack on phosphorus. Bromine will be leaving. So we are getting phosphorus carbon bond formation. Of course, the positive charge will be there. Counter ion is Br minus. Now another triphenyl phosphine will take another bromine so that it generates a negative charge on carbon. So the overall product here is negative charge on carbon and positive charge on phosphorus. So this is like a Wittig reagent, or we can write it as double bond triphenyl phosphine, right? It is like Wittig reagent, but with carbon is having 2 halogens. So in a Corey-Fuchs reaction, first we are generating a Wittig type reagent by the reaction between triphenyl phosphine and tetrabromomethane. triphenyl phosphine, unlike its nucleophilic reactivity, it attacks on bromine so that it generates a negative charge on carbon. Then carbon will bond to phosphorus. Then again, one more triphenyl phosphine will take the bromine so that it generates a negative charge on carbon. So finally, we have generated this phosphorus halide. So this is called dibromoethylene phosphorant. Now from this, you know the same story, right? The phosphorus halide reacts with carbon negative charge. It reacts with carbonyl carbon. Then oxygen will react with phosphorus. So like a 2+2 cycloaddition, it generates oxophosphate ring. It generates oxophosphate ring. This oxophosphate ring will undergo decomposition in such a way oxygen will be leaving with phosphorus and we are generating a double carbon-carbon double bond. So triphenyl phosphine oxide is leaving. Then we are generating a carbon-carbon double bond. And of course, so this is the first step. When we treat aldehyde with triphenyl phosphine and tetrabromomethane, it generates 1,1 dibromoalkene. From this, the second step starts. We will treat it with a strong base. This is the proton which can be picked up by base. Then this carbon hydrogen bond will be polarized towards carbon-carbon double bond. With the expulsion of one of the bromide, it generates a triple bond. It generates a triple bond. Of course, we know alkyl lithium reagents will pick up the halides, right? So one more alkyl lithium reagent will pick up the bromide so that it generates acetylenic anion. It generates acetylenic anion. Now we can convert this anion, we can quench this anion with variety of electrophiles, right? We can use H plus so that it becomes a terminal alkyne, or we can use any aldehyde or alkyl halide, a variety of alkyne, variety of electrophiles. Okay, so this is how we will convert a C double bond O into aldehyde group into alkyne under Corey-Fuchs reaction conditions. Generally, we use 4 equivalents of triphenyl phosphine, and the byproduct is triphenyl phosphine oxide, which is we have to separate it by column chromatography only, right? It will not dissolve in water, so we need to purify it during column chromatography. So it takes a lot of time to purify the compound. At the same time, it leads to pollution problems, right? So that is why we must reduce the use of triphenyl phosphine in this reaction. So for that, what we need to do is we need to add zinc dust to equivalents. Zinc will be converted to Zn2 plus, so it's not a polluting agent. So to reduce the triphenyl phosphine from 4 equivalents to 2 equivalents, what we will do, we will use zinc dust 2 equivalents. Of course, tetrabromomethane, it will not change. Under these conditions, yeah, we can generate this compound. So instead of 4 equivalents, we can take 2 equivalents if we use zinc dust. Then it will be converted to alkyne using two equivalents of alkyl lithium. It will be converted to this is the intermediate, right? So we have generated acetylenic anion. This acetylenic anion can be converted, can be explored in different ways, right? We can use a simple acid, water, a dilute acid. So in this case, the electrophile is proton. So anion picks up this proton, so it becomes terminal alkyne. But we can also use variety of electrophiles. For example, in this case, we are reacting this acetylenic anion with carbon dioxide. So what is the product here? The product is anion will react with carbon dioxide, so it becomes carboxylic acid. So in a similar fashion, we can use variety of electrophiles to treat with acetylenic anion. What is the product? This upon treatment with the platinum catalyst, toluene, 80 degrees centigrade, it gives this product. So this is Corey-Fuchs reaction, which converts aldehyde into triple bond. Now I will give you a sequence of reactions where we can convert a small molecule into a large molecule. So this will convert aldehyde into dibromoalkene. Then we will treat with alkyl lithium that converts this into alkyne anion. The anion is quenched with this electrophile formaldehyde triple bond. Then the anion generated is treated with formaldehyde, so it generates propargyl alcohol. Now propargyl alcohol can be protected or can be allylated using allyl halide. So allylation generates this compound. See, it is a good substrate for Wittig rearrangement. So when it is treated with N-butyl lithium, it undergoes 1,2 rearrangement. anion will be generated here. So it is 1, then it undergoes 1 2. So anion generated here will attack here, so this bond will break down. Okay, that generates anion generates here that will attack on this carbon, then this carbon oxygen bond will be polarized towards oxygen. So we generate this rearranged product. Now this rearranged product, yeah, alcohol is there, we need to protect alcohol. So what we will do, we can protect this alcohol with a silicon reagent, dimethyl aminopyridine and triethylamine, a mixture of bases. Of course, 2 methyl groups. Now you look at this, it is a very good substrate for radical cyclization, a tandem radical cyclizations. If we can generate a radical here that will cyclize with this triple bond, that generates another radical, that radical will undergo cyclization with this, right? So it is a very good substrate for a sequence of radical reactions. Now, how do we generate radicals from halogens? When we treat them with tin hydride, then we can generate radicals from alkyl halides. Now, as I said, 5-membered rings are more stable. So 1, 2, 3, 4, 5. So this radical will attack here. Then this radical will polarize towards this. This is called 5-exocyclic because it will be on the ring but outside the ring, and since the shape of the molecule, it is triple bond, so diagonal, so it is called 5-exo-dig. This we can obtain from Baldwin rules, which cyclizations are favorable, which cyclizations are unfavorable. So these things can be obtained from Baldwin rules, but you remember 5-membered rings can be formed easily. So when we do this, it is 5, then exo means this triple bond will be converted to double bond. Better I'll write the product and explain this. Yeah, see, after cyclization, this double bond, it becomes exo. So that is what it means, exo. Then dig means diagonal. The triple bond shape is diagonal. So cyclizations with 5-exo dig are favorable, which is explained by Baldwin rules. Then this will undergo cyclization. Now we need to count the ring size: 1, 2, 3, 4, 5. So the radical will add here. Now if you want to say what is this cyclization, it is generating a 5-membered ring, so it is 5. Then uh, uh, how this double bond is either it is inside the ring or outside the ring. It is outside the ring, so we call it as exo. Then what is the shape of this double bond? Trigonal planar, so that is why it is called trig. 5 exo trig. It is generating a 5-membered ring. So it is 5. And this alkene, it will be outside the ring. So it is exo. And the shape of this alkene, it is trigonal planar. So shortcut trig. 5 exo trig. So it generates this radical. Okay. Then this radical can be quenched with a proton source. Yeah, we are using tributyl tin hydride. So this hydride will be picked up by this carbon so that it becomes neutral. Then again this will involve in another cycle, right? Then I'm not writing the product. And finally, you just write the product. When we treat this with methyl lithium, what is the product? You write this. When we treat this with methyl lithium, what is the product? I'll give the product here. When we treat this with methyl lithium will attack on silicon. So silicon oxygen bond will break down. So it becomes trimethylsilane. This becomes OH.